Hi guys, and welcome to Module 7 where we talked about ratios, rates. In this lesson we talked about finding ratios from tables and graphs. And this first example talks to us about students in a science class. And the information given is that for every 5 milliliters of ammonia, it requires 250 milliliters of distilled water. In addition, the information given on this table is that for every 2 milliliters of ammonia, we need 100 milliliters of distilled water. So a lot of information given, and then our job is to complete the table. And we can do this several different ways. I think the best way that we should do this is in order to complete and fill in these blanks and complete this table, I think that we should determine the unit rate. So how much water will we need for every milliliter of ammonia? And I think that if we do that, that's probably the best way to go. So let's go ahead and write a rate where we have information given. 2 milliliters of ammonia to every 100 milliliters of water. And so if we want to find the unit rate, we're going to divide by 2 because we want to know how much water we're going to need for every milliliter of ammonia. So 100 divided by 2 is 50, which means we're going to need 50 milliliters of water for every milliliter of ammonia. Well, then that's easy because when they give us 3 milliliters of ammonia, all we have to do is multiply this by 3 in order to determine how many milliliters of water we're going to need. So 50 times 3 is 150. This half is interesting because we know it's 50 for every milliliter, so this includes a half, and so it's going to be over 150, but not yet 200. So half of 50 is 25, and so if we do 150 plus 25, we get 175. And then last but not least, we're given the amount of distilled water, and our job is to determine how many milliliters of ammonia that is. Well, we determined that for every milliliter of ammonia, there's 50 milliliters of water. So what we could do is take the water and divide it by how much ammonia each one needs, and that'll tell us how many milliliters of ammonia there are. And so we can go ahead and cancel out the zeros. That's our trick. And 20 divided by 5 is 4. And so the answer here would be 4, and we have completed the table. In this slide, we see the distance formula. We talk about distance, speed, and time and their relationship, how they are related. To find the distance traveled, or the D, you're going to have to multiply the speed, or the R, by the time, or T. So let's just talk about what these all mean. Distance is the amount traveled, and then your speed is at the rate at which you're going, and the T is the time that it's taking you to get there. So we're going to see some examples. I did tell you guys that you will have this distance formula given to you on the reference sheet. D equals R times T, or distance equals rate or speed times time. So you don't need to memorize it, but you certainly need to know how to use it and how to apply it. So let's take a look at an example where we would have to find the distance. If we're given a falcon can dive at a speed of 80 meters per second, that is important information. And the question is asking us how far can it dive in 4 seconds. That's also important information. So what we should do is set up a rate where we write a rate for the given information. This falcon can go 80 meters for every 1 second, and the question is asking us how far can it dive in 4 seconds. So we go ahead and set up this rate, and we match up the units to the unit together, so the seconds to the seconds. And so we talked about to get from 1 second to 4 seconds, are we getting bigger or are we getting smaller? Since we're getting bigger, we know we're going to have to multiply. Well, 1 times what will give me 4? And that's 4. What I do to the denominator, I must do to the numerator, and so 80 times 4 is 320 meters per 4 seconds. Now, in order to find the distance, we have to multiply the rate or the speed times the time. And the inverse operation of multiplication is division. So if we wanted to find the speed at which something is going or someone is going, we would have to take the distance and then divide that by the time, and that will get us the rate. So let's take a look at an example where we would have to determine the distance. The table shows the distance that Randy drove on one day of her vacation. The question is asking us to find the distance that Randy would have gone if she had driven for one more hour at the same rate. So very important that we are able to understand this information given in this table. And this table is really telling us that for every hour, Randy is driving 55 miles. So that's actually already giving us the unit rate. She's traveling 55 miles per every hour. So in order to determine how many miles she has traveled in 2 hours, you can either take 55 and multiply it by 2, or since this is a table, you can continue to add 55. So in 3 hours, she's traveled 165 miles. In 4 hours, she's traveled 220 miles. In 5 hours, she's traveled 275 miles. So you can answer this question one of two ways. You can either take the 55 miles per hour and multiply it by 6, because the question is asking if she had driven for one more hour, then how far would she have gone? So we can take the 55 miles times the 6 hours, and that will get us to 330 miles per 6 hours. Now, when we did this question in class, some of you decided, hey, since I already have that she traveled 275 miles in 5 hours, I could just add another 55 miles because we're only going one more hour, so adding another 55 miles. And so regardless of whatever way you decide to do it, you will get that if Randy would have gone another hour at the same rate, she would have traveled a distance of 330 miles. We also talked about proportions, and we stated that proportions are statements that two ratios or rates are equivalent. So here are some examples. 1 to 3 is proportional to 2 to 6 because they are equivalent ratios. So for this example, we need to determine whether these two ratios are equivalent or determine whether they are proportions. And the information given is that on the first day you pay $5 for 2 boxes of popcorn. So I'm going to go ahead and write that as a rate. I'm going to write $5 for 2 boxes of popcorn. And then the question is asking me if I pay $7.50 for 3 boxes, is this proportional or are these two ratios equivalent? What I'm going to do to solve this problem is I'm going to divide by 2 because I want to find the unit rate. I want to know how much I'm paying for each 1 box of popcorn. And so $5 divided by 2 is $2.50. And so I am paying $2.50 for 1 box. Now I want to see if this is proportional. If I pay $7.50 for 3 boxes, well, if I go ahead and multiply by 3, $2.50 times 3 is $7.50 for 3 boxes. And so the answer here is that yes, these two ratios are equivalent or they do form a proportion. We also talked about in class how to determine whether ratios form a proportion by comparing the ratios in simplest form. So for example, if we have the ratio 6 to 4 and we want to write that ratio in simplest form, we would determine that the GCF is 2. And so if we divide by 2, the equivalent ratio of 6 to 4 is 3 to 2 in simplest form. Now, if we did the same thing for 8 to 12 and we determined that the GCF between 8 and 12 is 4 and we divided by 4, we would get a ratio of 2 to 3. So these 6 to 4 and 8 to 12 By comparing the ratios in simplest form show that they do not form a proportion because the ratios are not equivalent. Yet another way to determine whether ratios are proportional is to cross multiply. So in this case, they tell us if you swim your first 4 laps in 2 4/10 minutes, and then it says you complete 16 laps in 12 minutes, is the number of laps proportional to your time? What they're really saying is go ahead and set the information given up as a rate. So we swim 4 laps in 2.4 minutes. And they're asking us, is this proportional to your time if you then swim 16 laps in 12 minutes? So what we can do is we can cross multiply. We can multiply 16 times 2.4, and that'll get us 38.4. And then we can cross multiply 4 laps times 12 minutes, and that'll get us 48. Since these are not equal, the cross products are not equivalent, therefore the number of laps is not proportional. We had fun with these types of problems in class. It's telling us if Sheldon makes $2 in profits for every $5 that Leonard makes. Then it tells us that Leonard makes $20 in profit on the first item that they sell. How much profit does Sheldon make? Well, this was very, very simple. We said we were going to set this up as a ratio where we have the $2 that Sheldon makes for every $5 that Leonard makes. And then the information given is that Leonard makes $20 in profit. So we go ahead and match up Leonard with Leonard. And so this is very simple from this point forward, because now we say, well, to get from 5 to 20, are we getting bigger or smaller? We're getting bigger, so we know we need to multiply. 5 times what is 20? What I do to the denominator, I must do to the numerator. And so Sheldon made an $8 profit. Again, I noticed you guys really enjoyed rates and ratios. You guys did a really nice job with them. In this example, if the important information is that for every 2 cheese pizzas, we order 3 pepperoni pizzas. So how many cheese pizzas would they order if they ordered 15 pepperoni? So again, as long as you're setting this up as a rate, and then you are matching up your units, so pepperoni with pepperoni in this case. And then we have to determine to get from 3 to 15, we're getting bigger, so we know we're going to multiply. 3 times 5 is 15. What I do to the denominator, I do to the numerator, and so 2 times 5 is 10, and my answer is 10 cheese pizzas. In this example, we see the importance of using unit rates to solve proportions. The information given is that this person runs 3 miles in 36 minutes, and that information is given right here. 36 minutes shown on the pedometer. So here it is, 3 miles for 36 minutes. So the first thing we would do is write this as a rate or as a proportion. 3 miles to 36 minutes. And then our step 2 would be to find the unit rate. And so we want to know how far this person, how many minutes it's taken this person to go 1 mile. So it's taken Ali, if we divide by 3, we're going to go ahead and determine that it takes him 12 minutes to go 1 mile. And then the last step is to take the unit rate, which is the 12 minutes per 1 mile. And then the question is saying at this rate, how far could he run in 60 minutes? So again, we match up the minutes to the minutes. So what we've determined so far is that it takes Ali 12 minutes to run 1 mile. And so if the question is asking at this rate, how far could he run in 60 minutes? I'm going to go ahead and match up my minutes to my minutes. And so to get from 12 to 60, I know that I'm getting bigger, so I multiply by 5. And what I do to the denominator, I do to the numerator. And so Ali, at this rate, can run 5 miles in 60 minutes. This is another example of when we would find the unit rate in order to solve problems with proportions. So in this example, we have Miss Reynolds' sprinkler system has 9 stations that water all the parts of her front and her back lawn. Each station runs for an equal amount of time, and if it takes 48 minutes for the first 4 stations to water, how long does it take to water all the parts of her lawn? The first thing I'm going to do is I'm going to set this up as a rate. So it takes 48 minutes to water 4 stations. And the question's asking, how long does it take to water all parts of her lawn? Well, her lawn has 9 stations. So unfortunately with this one, there is no 4 times anything that'll get me to 9 as a whole number. So the easiest way to do this is to determine the unit rate. And so we have information given. It takes 48 minutes to water 4 stations. So let's divide by 4 to see how long it takes to water 1 station. Well, 48 divided by 4 is 12, so it takes 12 minutes to water 1 station. And the question is asking, how long does it take to water all the parts of her lawn? Well, her entire lawn has 9 stations, so we're going to go ahead and multiply by 9, and that'll get us to the 9 stations. And 12 times 9 is 108 minutes to water 9 stations. In class, we talked about the importance of scales and keys in a map. Obviously, the distances that are described in maps are very, very large distances, and so it is important to be able to read the scales and keys on a map. In this case, they tell us that to get from Sandville to Lewiston, it takes there is a distance of 2.5 or 2.5 inches. Well, obviously, you know that that isn't the case. You know that you have to look for a scale and determine how many miles are in 1 inch. And if we do that, this is the most important place to begin with a question like this. We see that it takes 1 inch is equivalent to 20 miles. So what we would have to do is we would write this as a rate. We would say 1 inch in this map represents 20 miles. And in this example, between Sandville and Lewiston, we see a distance of 2.5 inches. And we would go ahead and match this up yet again, inches to inches. And to get from 1 to 2.5, we know we're getting bigger, so we're multiplying by 2.5. And so we go off to the side and we go 20 times 2.5. I would probably just do 2.5 times 2 and add the 0 at the end. So that'll be 5. Don't forget your 0, and then don't forget to bring over your decimal. So the answer here is that the distance between Sandville and Lewiston is 50 miles. In Module 7, we also talked about customary versus metric measurements, and we talked about customary being the system that we use in the United States, whereas in other parts of the world they use the metric system. And so in this lesson, we talked about conversion factors and how if conversion factors is just a rate that equals 1. So for example, if we're talking about customary measurements and the ones that we use in the United States, a conversion factor would be 1 foot is to 12 inches because they equal 1. If we were talking about the metric system, for example, we would say 1 meter is to 100 centimeters. And so these are conversion factors because they are rates that equal 1. In class, we also had a really nice time drawing the gallon house, and I told you guys that the gallon house was really simple, and you are going to have the reference sheet with the conversions and the conversion factors on there, and so you really don't have to memorize it. But with something like these kind of units where you're talking about pints and quarts and cups and gallons, those are pretty standard, and so we should know those. So we went ahead and we drew a gallon house, and we drew the big house, which was the G. And then we went ahead and gave this house some windows, which were our quarts. And that means that there are 4 quarts to 1 gallon. And then we said that in each window we had 2 people looking out the window. And that shows many different things. That shows there are 1, 2, 3, 4, 5, 6, 7, 8 pints to a gallon. It shows that there are 2 pints to 1 quart. It shows that there are 1, 2, 3, 4 pints to a half gallon. And then the last thing that we want is to give our people some eyes. So we go ahead and give them their eyes. And those represent the cups. So what we can determine from here is that we have 1, 2, 3, 4 cups in a quart, or 4, 8, 12, we have 16 cups to a gallon. So this gallon house gives us a lot of important information, and we had a good time drawing it in class. So when we're converting units, it's very important that we understand the conversion factors, and we can easily get those from the reference sheet. So again, we don't have to memorize this, but if, for example, they're telling us to convert 36 quarts to gallons, what we can do is write the conversion factor, and we get this from the reference sheet, or we can get this from the gallon house, where we see that 1 gallon is to 4 quarts. So again, we would match up our quarts, and so to get from 4 to 36, we know we're getting bigger, so we multiply times 9, and what we do to the quarts, we do to the gallons, and so we know that there are 9 gallons to 36 quarts. And this is just an example of the conversion sheet or reference that you have in your spirals, and this one does break it up into your customary measurements, the ones used in the United States, and then on a separate space they give us the metric measurements, which are utilized in other parts of the world. So staying with the notion of converting within measurement systems, if we are asked what is the weight of a 3-pound human brain in ounces, we would need to know what the relationship or the proportion is, or the conversion factor is, between ounces and pounds. And what we get from our reference sheet is that there are 16 ounces to 1 pound. And so if they tell us that the weight is 3 pounds, again, we would match up our pounds. And to get from 1 to 3, we multiply by 3. And so 16 times 3 would be 48 ounces. This conversion, on the other hand, is between measurement systems. So this one is converting between customary to metric, and so it's no longer converting within measurement systems where all the customary were together and all the metric were together. Now we're combining the two. Now we're intertwining the customary and the metric in one system. So there is only one measurement that is exact, and that is the 1 inch is to exactly 2 54/100 centimeters. Everything else is an approximation, because since we are converting between systems, then it's only very, very, very close, but the measurements are not exact. So looking at an example where we convert between measurement systems, they give us a sheet of paper. If it's 11 inches, what is this length in centimeters? So again, this inches is customary, and they want us to change it to metric, which is centimeters. So we have to know the conversion factor, which we can get from our sheet, our reference sheet. 1 inch is to 2 54/100 centimeters. And if we write this as a rate, so we go, or a proportion, we go ahead and write 1 inch to 2 54/100 centimeters. And we're given that this sheet of paper is 11 inches. So again, we match up our units, so inches to inches. To get from 1 to 11, we multiply by 11, and 2 54/100 times 11 is 27 94/100 centimeters. Another example of converting between measurement systems is if John was in a different part of the world and he realized that he added 11 3/35 kilograms to his bar, and he came back to the United States and his friend said, "Hey, what's that in pounds?" He can very easily do that by finding the conversion factor. So from the reference sheet, we know that 1 pound customary is approximately 454 thousandths of a kilogram, and that's metric. So if he added, so we go ahead and we write that as a rate. So 1 pound is approximately 454 thousandths kilogram. And they tell us that he added 11 3/35 kilograms. So we would match up the units here. And to get from 454 thousandths to 11 3/35, that is not very simple to do. So you're going to have to take the 11 3/35 and you're going to have to divide that by 454 thousandths. And we know that we cannot divide with a decimal as the divisor. So the rule is you take that decimal point, you move it to make it a whole number, 1, 2, 3. And so what you do to the divisor, you do to the dividend, 1, 2, 3. And so the new setup is 11,350 divided by 454. And the answer to that would be 25 pounds. I hope you enjoyed our review of Module 7. If you have any questions, please feel free to ask.